Number 4 from 2-9. That's a good one. Trying to choose the good ones. Okay, so it says, given below is a matrix A and an echelon form of A, find bases for the column space of A and the null space of A, and then state the dimensions of these subspaces. So let's write down A first. And then they say that this is row equivalent to this other matrix, which is in echelon form, not reduced echelon form, just echelon form. Okay. So a basis for the column space of A is what? Okay. Now, one of the facts that you need to use on this problem is that the number of pivot columns in the echelon form of the matrix is the same as the dimension of the original column space of the matrix. So in other words, notice that in echelon form, the first column is a pivot column. So is column number 3, and so is column number 4. So there are 3 pivot columns in the echelon form of the matrix. That gives us the dimension of the original column space of the matrix. You just kind of have to use that fact. And you can choose the original columns of the original matrix for those basis elements. So in other words, my basis, or a possible basis for the column space, since since the echelon form, the first column is a pivot column, I can use the first column of the original matrix as a basis element. So that's one of the 3. The third column of the echelon form was also a pivot column, so I can use the third column of A as another basis element of the column space. And then the fourth column of echelon form was also a pivot column. So that means I can use the fourth column of the original matrix as a basis element. So you just kind of have to use that fact. So there is a basis for your column space. All right. All right, so in the second part of the problem, we're supposed to find the null space of A. So there's part A, there's part B. Now we're looking for, and let me see if they wanted a basis for this thing. Let's see. Yeah, they actually wanted the basis for the null space of A. Okay. So just remember, the null space of A is the set of all vectors that will map this thing into 0. So let's write down matrix A. So the set of all vectors x1, x2, x3, x4 that make this true, those vectors form the null space of A. Okay. All right. So let's solve that system in general, and then we'll try to determine the basis or the dimension of that vector space, that subspace. Okay. And as always, we're going to do this with an augmented matrix. I'm going to use a calculator though, because we already know how to do it the hard way. So let's see what this thing turns into with a calculator. So let's see. Let's see if we can remember how to do it with a calculator. Hopefully you can see that. So the first thing you want to do is enter the matrix into your calculator. So go to matrix above x to the -1, Scroll over to edit. That's how you enter a matrix. We'll call this thing A. It is a 4 by 1, 2, 3, 4, 5, 5, 4 by 5. Okay. So let me enter the elements. And now I'll escape out of there because I want to go back to matrix. And then we'll go over to math. That's where you do calculations. And scroll up to reduced row echelon form. And really, echelon form is probably enough. So I'm just going to choose reduced echelon form. But let's put it in reduced echelon form just to be safe, because we actually want the solutions of this thing. So let's do that. Reduce row echelon form of A. So go back to matrix, but this time choose names A. Close your parentheses. So it looks like it's this matrix. All right. So this is a set of vectors, and we have to characterize this solution set. And once we characterize it, we can determine the dimensions of it. And they actually wanted the basis for it too, so I guess we need to come up with a basis for this vector subspace. All right, so first of all, what are our basic variables? Well, it looks like that's a pivot column, that's a pivot column, and that's a pivot column. So it looks like we have 3 basic variables. And the basic variables are x1, x3, and x4. x2 is free. We have 1 free variable, which is x2. All right. But let's write this as a system of equations. This says x1 plus 4x2 equals 0. So that means, remember, when you characterize infinitely many solutions, solve for the basic variables in terms of the free variables. So that'd be negative 4x2. The second equation just says, well, it just says x3 equals 0. So x3 has to be 0. Let's see what else. And it looks like x4 also has to be 0. Okay. But x2 is free. So let's characterize that with a single vector. It's a 4 by 1. Remember, every solution looks like a vector of this form because it's in R4. But x1 is negative 4x2. x2 is just x2 because it's free. x3 is 0 and x4 is 0. So I suppose we could factor out the x2. That'd give us negative 4, 1, 0, 0. So it's the set of all these vectors, and it looks like that is a vector space with 1 dimension. All right, because we just have 1 vector. It's linear combinations of just 1 vector, so the dimension is 1. But the basis of this thing is just going to be this. That's the answer, really. That's the basis of this null space of A. All right, you know, one of the interesting things about this is you might recall from the first part that we had 3 basis elements, and this time we just have 1 basis element. And I just want to make an observation. Whenever you do a problem like this, this equation should always be satisfied. The dimension of the column space of A plus the dimension of the null space of A should be equal to n. And I'm assuming here that your linear transformation takes Rn to Rm. Okay? So your matrix A should take n-dimensional vectors into m-dimensional vectors. So let's recall what A was in terms of size. It was a 4 by 4, I think. Yeah, it was a 4 by 4. So if what I said is correct, then the sum of these two dimensions ought to be 4, because n in this case is 4. All right? That's really your n right there. So is that true? And the answer is yes, because the dimension of the column space was 3. We just found the dimension of the null space is 1. And the sum of those two is 4. Sometimes on these kind of problems, they'll give you 2 of the 3 numbers, and they'll ask you to find the other number. But just remember, you always assume that you're mapping elements in n-dimensional space into elements in m-dimensional space when you use this equation. And that constant on the right-hand side is always n. It's really the number of columns in your matrix A is what it is. It just so happens in this case, n and m were the same number, 4.